Welcome to our investigation into geometry extremas. I am Yuheng, your technical editor and coordinator. We will prove the extremas of modulus and argument through rigorous manual algebra and visual tangency. Let's begin.
Assalamualaikum. Today I'll be doing circle. So for Cartesian expansion, I chose the z-node value and r equals 2, and I got the circle center and the radius. For the modulus extrema, I found the modulus of z-node, where I substitute it into the given formula with the minimum and the maximum z value. And then for the general proof of the minimum and max, we got extremes occur along the direction of z-node, unit vector over z-node, and we can move r forward or backward. Now for the argument extrema, we're supposed to substitute y equals mx into the circle equation, where once I did that, I got a quadratic, where I factorized it to quadratic. And then for the discriminant, we're supposed to set it to equal 0, so we took that quadratic and substituted it into the discriminant, where I used the quadratic formula to find the values of m, where m2 is the max and m1 is the minimum. And then for the last one, we find the argument of z, where it's the inverse tangent of the minimum and the maximum, where the minimum I got 29.6 and maximum 76.7.
Okay, so today we are proving ellipse. So first we choose z1 and z2. z1 is 5 and 0 and z2 is negative 5, 0. So a is much greater than sum of z1 and z2. So a equal to 26 is greater than 10. So after that we sub into the formula and we can solve the algebra here. And after that we should sub the z equal to x plus yi. And after that we should get this, and using the Pythagoras identity, and we can prove the equation. Since our center is 0, 0, so h and k is 0. So the equation is proven.
Okay, so moving on, we need to find the modulus extrema, which is the minimum or maximum value of a function. So first of all, we need to find dy dx through implicit differentiation. So this equation is the equation we are given, the equation of the ellipse, and then we differentiate it, and to find it, the dy dx. So next up, we need to differentiate the function of distance, and then after differentiate it, we will get the dd dx in terms of x, y, and dy dx. And then next up, we are going to find the minima and extrema. So for the minima, we need to set the dd dx equals to 0, and then substitute in the dy dx value we found earlier, so we can get the value of x equals to 0. By substituting the value of x equals 0 into the ellipse function, we can get the value of y, and then we can get 2 points. So these 2 points, we substitute it into this equation, and then we can find the z value equals to plus minus 12i. And then we modulus it to get 12, and this 12 will be the minima of the minima distance of the ellipse. So next up, we need to find maxima. But in this equation, we need to have a different approach. Why? Because as you can see here in dy dx, we can't substitute y equals to 0, otherwise the dy dx will be undefined. So instead of doing what we did earlier, we need to substitute y equals to 0 into the ellipse function, and then we can find the value of x. And by using both points, we can find the maxima of the ellipse, which is the maximum distance between a point in ellipse with its center.
My name is Wong Jiajin, and I'm in charge of the role of the GeoGebra archetype. In GeoGebra, we visually verified these calculations. As we can see here, the locus is projected here, and a sweeping circle, which starts from the origin, it touches the locus exactly at r equals to 3, and perfectly inscribes it at r equal to 7. Besides that, the tangent rays y equal to 0.567x, as well as y equals to 4.233x, perfectly grazes the circle's edge, which confirms our angle. Now, as for our centered ellipse, as shown here, the sweeping circle which starts from the origin, it first touches the top and bottom at exactly r equal to 12. And so we can see top and bottom, which confirms our z minimum. And then it completely engulfs the left and right edges at exactly r equal to 13. Left, right. This confirms our z maximum. Furthermore, any straight line from the origin cuts through the ellipse. As we can see here, any straight line, it cuts through this ellipse, which visually proves why our tangent discriminant was imaginary.
Comparing our methodologies and visual algebraic proofs align perfectly. For the circle, our manual extremas are mirrored exactly by the GeoGebra tangent coordinates. However, the elliptical locus presented a unique boundary condition. When optimizing the argument extrema algebraically, the discriminant yielded an impossible result. Rather than a calculation error, this mathematical anomaly is perfectly explained by our visual model. The origin is trapped entirely inside the ellipse. Because of this, a definitive tangent line geometrically cannot exist. Through this dual verification process, our geometric extremas are definitely confirmed.